Yes, my name is Paul Pickard. I am at Sandia National Laboratories in New Mexico. Sandia is one of the three laboratories run by the National Nuclear Security Agency. As with this lab and the sister labs at Los Alamos and the one here in California at Livermore, these labs have a wide variety of activities going on in energy research, defense. One of the things we have done at Sandia in the last 20 and 30 years is a program to support the Nuclear Regulatory Commission in reactor safety studies. These involve both experiments to study particular events, but also systems analysis to look at reactor safety issues. So it's that kind of context from this reactor safety point of view that we are using to do our study of the SRE accident. The purpose of my presentation this morning is a little broader than the others. I'm going to try to provide some background information on the SRE, the design of the reactor, the things that went into the design of that experiment, particularly those that are relevant to the accident that occurred in July of 1959, as well as then a description of the accident, a kind of a general description of the accident, what went on, and then a brief evaluation from our point of view of what we observed from that. As Kevin mentioned, this review did focus on the events of 1959. We did not look at the events before that in any detail other than to set the context for the accident itself. We did not look at the recovery operations either. So this really focuses on the event in the July timeframe of 1959 that resulted in significant fuel damage to the reactor. The range of information available here was provided to us is quite broad, lots of documents. On the other hand, this was 50 years ago. Not everything is complete. Things are somewhat difficult to find. Not every piece of data was available readily. So I think all three of us did the best we could looking at the documents and selecting the information we thought was the most relevant. This is the outline of my presentation, a little bit of background, a description of the design of the reactor, description of the accident, and then a discussion of the fuel damage and the resultant fission product release. The picture that's shown here in this is the picture of the SRE site in 1958, showing the reactor building, the large high bay building in the upper center of the picture, cooling towers in the lower picture, the support facilities and energy conversion facilities that were there. Of course, we had the opportunity to visit this site yesterday, touring with many of the workers from that period of time. And of course, now it is, all the buildings have been removed and replaced, and it's now a empty field. But it was certainly interesting to hear the former workers talk about the events and activities that went on at that time. Just to provide a little bit of context for this accident occurred in 1959. The reactor was designed in the mid-50s and went operational in 1957. That was a very early stage of nuclear energy development. If you recall, Eisenhower had introduced Atoms for Peace in 1953, a major national initiative to look at the potential of nuclear energy for the use of electricity generation. The Navy had already started using nuclear reactors for submarines. The Nautilus, I think, was launched in 1954. And reactors were already being commercialized. People were already looking at those. As early as 1957, the first commercial nuclear plant generating electricity shipping port was started in 1957. This is a 60 megawatt electric plant compared to today's plants, were typically in the 1,000 to 1,500 megawatt range. This is very small. Of course, there are something like 400 nuclear power plants operating around the world. 100 of them are in the US. All of these plants use the same light water cooled technology, using a light water coolant to cool the nuclear fuel that is generally gone through a heat exchanger, a steam generator, to generate steam for electricity. These plants are quite large. The technology has now been pretty well developed. It is very complete now. so that these 400 plants and almost everybody in the world uses the same technology for light water plants, with very few exceptions. However, the light water plants have some characteristics, one of which being they operate at relatively low temperatures because the pressures are very high. In the 1950s and the 1960s, it was recognized that pressures of 2200 psi, very, very high pressures, were a limitation. That was going to require very large pressure vessels, sophisticated technology for that, and it also limited the efficiency. The lower the temperature, the lower the efficiency. They were looking for ways to achieve higher efficiency, which meant coming to higher temperatures. And sodium reactors presented that kind of an opportunity. Sodium boils at a much higher temperature, so sodium-cooled reactors, particularly those with graphite moderators, were considered one of the promising alternatives to light water reactor technology. So these things could operate at much higher temperatures and therefore higher efficiencies, possibly being more cost effective, but they would also still operate at very low pressure since there was no boiling to cause pressure. So the experiments in Area 4, the Santa Susana site, those were focused on the development of these sodium-cooled reactors. The SRE was the largest of the reactors that were built in the 1950s and 60s at Santa Susana. It was a 20 megawatt facility. Most of the other test facilities at Santa Susana were much smaller, and they were generally intended to be test facilities for radiation or component development, including some of the SNAP reactors, which were intended for space nuclear applications. So the sodium reactors that were developed here took advantage of these characteristics of sodium. The high boiling point meant that the reactor could operate at low pressures, even at much higher temperatures. It's an excellent heat removal medium. This is a liquid metal. It's much better than water at removing heat, but these benefits come at some cost. The sodium is flammable in air. It oxidizes readily. It reacts with water. It is sensitive to the contaminants in the sodium coolant, so it requires a much more sophisticated technology in general than light water reactors do. And that was the challenge that was addressed in these experiments, is to look at how you might use the sodium coolant in the reactor. So we'll move on and talk about the description of this reactor. The reactor itself is located in the high bay structure, large several-story high bay structure with cranes to allow positioning of fuel. The reactor itself is this small cylinder in the bottom of that facility. The reactor itself is located underground, was located in about a 20-foot deep tank of sodium that was covered by a concrete plug, and then that was the access to the top of the reactor facility. So in this high bay facility, there was access to the high bay. You could access the high bay for both insertion and removal of fuel rods. The purpose of this reactor was to evaluate the performance of nuclear fuels. So there was many times where the fuel would be inserted or removed, so they had to have ready access to the reactor facility. And this plug, we'll show a better picture of that, was the access port that was used to do that. In this facility, of course, there are facilities to have fuel handling capabilities. When you remove the fuel, they would have a fuel cask. That is the device shown over here on the left. There was a small hot cell facility in the back of the reactor building to support the inspection of the fuel. The typical operations, I think, were irradiation of the fuel and then removal for inspection to see if there had been any operational impacts on that fuel. The stack that's actually shown at the top of this picture, the very high, was the one that was used to vent the radioactive materials that would be collected in the cover gas or other areas where there could be radioactive gaseous products. The control room was located right in this facility. The sodium pipes that run through this then are actually underground. They are in things called galleries. They were run through concrete galleries. Because sodium is oxidized readily, those galleries were generally inerted, meaning they removed the oxygen from those so that the gaseous products would not react with the sodium should there be a leak. And so the primary feature here is this sodium tank of about 20 feet in depth. And I've shown a little better picture of that here, showing the reactor core and the sodium tank here. The sodium tank is about 11 feet in diameter. It was a little less than 20 feet deep, lined with a stainless steel tank. This schematic diagram only shows one tank, but there were actually two tanks. There was a core tank that's shown here, some insulation between that, and then an outer tank, so that if the inner tank ever leaked, the sodium would be captured in the outer tank and not uncover the overall reactor core. The reactor core in the active part is shown here is about 6 feet. It was about 6 feet high and about 6 feet in diameter, but the actual fuel grid, the structure of the fuel grid occupies the entire width of the tank, and we'll show a better picture of that. So the major features here, there was a grid plate that supported the fuel elements. The fuel elements then are fed sodium from the bottom. They go up through channels and are cooled at the top. The sodium tank is deep enough to have about 6 feet of sodium above the tank, and above that region is something called the cover gas. Wherever there was active sodium in this system, they provided inert gas, in this case helium, to provide an atmosphere above the tank that could then be pumped in case there were radioactive materials that got into the gas above the system. The concrete plug sits above that. This is a very heavy concrete plug. It's shown over here. It's, I think, weighs something like 75 tons. It was there to provide shielding for the workers that might be in the reactor room working with the reactor or removing fuel. There are many penetrations in this. Control rods had to be penetrated through this. And in this plug, it's not very easily visible right here in the middle. There is an inner plug, and there were a couple of inner plugs that when you wanted to get to the reactor core and remove fuel, you had to remove those cores. They would put the fuel handling cask over that. They'd pull the plug and remove the fuel, and that's how they got in and out of this. So this plug is a plug, but it has many penetrations. And as you'll see later on, there were often leaks. There have to be seals with all these plugs. So these are real-time devices that have penetrations and potential for leaks along the way. So this is the basic configuration of this, and I wanted to describe the core, which is shown in the block in the middle here a little bit more in detail. This is a top-down view. This image in the bottom left is a top-down view of the reactor core. It is actually made up of a series of assemblies that include a large section of graphite moderator, graphite there, excuse me, to provide a means of slowing down the neutrons so that you can make better use of the nuclear fuel and end up with less nuclear fuel. Excuse me. So this top-down view is a series of these arrays of hexagonal graphite-filled cans with a fuel bundle of several rods in the middle of it. These graphite cans that are shown here are about 11 inches in diameter, so if you look across this core, you see that the ones with the blue dots are the ones with fuel in them. There are about 43 of those that were in this core that had fuel in them, and that's about 6 feet in diameter. The ones around the outside are simply graphite. Thank you, Kevin. The ones around the outside are primarily graphite, and they serve as reflectors. Excuse me, I'm very sorry. They serve as reflectors for the neutrons to, again, make the reaction somewhat more efficient. The assemblies themselves, these moderator cans and fuel bundles, these were hexagonal in shape. There was graphite that filled this. A central tube went down to allow the fuel bundle in, and the entire graphite hexagonal piece was then surrounded by zirconium metal. Zirconium metal is the same material currently used in light water reactors for cladding, so it is a commonly used material today. The fuel bundle in the middle here is shown in the upper right-hand corner. Fuel bundle was a relatively small amount of fuel. When you look at this core from the top, most of this area is graphite. Most of the fuel is graphite. So it was these small, nominally 2.5-inch diameter holes through the middle that contain the fuel. So when you look at these 43 elements, most of the material you see in the core is graphite. The fuel was contained in these fuel bundles that were inserted into these graphite elements. One of the features that is relevant here also is that when they first did these graphite experiments, they found that when they heated up the graphite, irradiated it, there were impurities in the graphite that would be activated, sometimes be gaseous. They would pressurize the can, the zirconium can, and that could fail the can or make it difficult to insert or take out. So they put a vent tube, which is shown here. Vent tube is open at the bottom. It allows gases that are created inside the moderator during the operation of the reactor to then be vented up through the top. These vent tubes then went above the sodium cover gas and exited in this gaseous region above the sodium. This allowed them to operate without worrying about failure of the graphite cans from that perspective. The fuel bundle here is described a little better in the next picture here. The fuel for this core, the core that was in the reactor at the time of the accident, was uranium metal fuel. It was just uranium metal. There were experimental elements in this fuel that actually had other materials in them, uranium with alloys or uranium thorium, but the majority of the core was simply uranium fuel enriched at about 2.78%. There's a relatively low enrichment. Uranium, when it's mined, comes with about 99% of U-238, the heavier isotope, which does not fission, does not react readily to neutrons in fission. About 0.7%, less than 1% is U-235. Almost every reactor in operation needs a little bit of enrichment to make the reactor critical, to make the nuclear chain reaction go. And the SRE had enrichments of 2.78%. Current water reactors today, the 100 reactors we have, are in the range of 4 to 5%. So it illustrates the relatively efficient use of the nuclear fuel using graphite, which allows a quite low enrichment. The fuel is contained in 6-inch long slugs. They called them fuel slugs. Illustrated over here, these were 6-inch long cylinders, 3/4 of an inch in diameter and about 6 inches long, that were made up of this pure uranium metal. You'd take 12 of those 6-inch long fuel slugs, put them in a stainless steel tube that surrounded them, and that would allow them then to form a fuel element that was sealed. Then 6 of the rods that were formed here were put into a bundle affixed with fittings on the top and the bottom that provide centering for the fuel channel and also then provide the spacing for the coolant to go through. You can see from this diagram up on the top here that the spacing of these fuel rods was quite close. There was less than 1/10 of an inch difference. Sodium is a very good coolant, so you did not need much room, but this was a very tight fit. You did not want elements bowing and touching each other. That would restrict the flow. So they put a wire wrap, and you can, I don't know if it shows up from your picture or not, but there's a wire wrap that spirals around each element that then touches the other elements at one point, but it maintains that nominally 90 thousandths of an inch spacing between the elements so that the coolant can penetrate up through the coolant. One of the things you observe here is that this was a fairly tightly packed channel. It was a small fuel channel, and it was pretty much like full of fuel. There was not much space for coolant or other things to go up. And that'll figure into the relative ease of which blockages could occur when foreign materials got into the core. The stainless steel cladding that is on the outside of the elements then provides a gap between that and the clad. And in order to minimize the amount of temperature difference between the coolant and the clad, they actually put sodium-like materials. This was sodium potassium, which is a lower melting version of the same kind of material. It's active metal, liquid metals. So this NaC or sodium potassium material was then inserted inside the rod, and that thermally bonded the fuel slugs to the sodium cladding, making the heat transfer out of the fuel element more efficient. So as a result, unlike the water reactors today, the temperature differences between the coolant on the outside and the fuel on the inside was not very great. There was very effective heat transfer so that the temperatures of the coolant were very close to the fuel temperatures. Whereas water reactors, which have coolants in the neighborhood of 300 degrees C, often have centerline fuel temperatures well above 2,000 degrees C because it's not nearly as effective a means to get the heat out. So these are kind of unique features of the sodium reactor technology. Just a comment on the cooling. Sodium flow would then be by the fuel element on the outside. The sodium flow, I believe, was in the 1,000 gallon per minute kind of, or per hour, 1,000 gallon per hour kind of range. No, 1,000 gallon per minute. I think that's right. Anyhow, that translates to about 5 feet per second, which sounds quick, but that's only a few miles an hour. So it is not a very challenging reactor to cool. The sodium is very effective at doing that. Nominal flow rates through the core then provide effective cooling. The sodium coolant went into the reactor at the bottom here at about 500 degrees F. It went up through the reactor and gained about 500 degrees so that the outlet temperature at the design powers was in the neighborhood of about 950 F. So significant temperature rise between the bottom and the top of the core with fairly modest temperatures. Coolant would flow in from the pumps on the outside of this, flow into the bottom plenum. Then there were orifices or holes in the bottom of the plate to allow the coolant to flow up by the fuel element. Another very important system, especially when talking about the accident and the fission product release, is the cover gas and venting system. I'd mentioned that in the system, in the reactor, if there were impurities or if there were a pinhole leak in a clad so the gaseous fission products would get out of the fuel, out of the sodium, that was captured in the cover gas, the gas space above the sodium in the reactor. All surfaces that interfaced with sodium had some kind of inert gas material, and this gas material was expected to be radioactive, at least at some level. So there were provisions made to pump this radioactive material periodically into storage vessels. These vessels were large vessels underground. They pumped that material into the storage vessels, waited for a period of decay, and then those vessels were routinely vented up through a stack, a filter in a stack, to the atmosphere. The regulations at the time were basically based on the amount of material you could release was some fraction of the background material that was there. So these were things that were done generally routinely during operation to vent the radioactive gases that collected in the cover gas above the reactor or other points in the cold traps or other points in the system that would then be released through this venting process through the decay tanks. The tanks were monitored when they were considered decayed to a sufficient level. They were then vented through the system. Obviously, when you look at the primary boundary, you look at the barriers to releasing fission products, this entire system then becomes part of that boundary. The vessel itself is part of that boundary, but all of these paths that lead to a radioactive path to release then are part of that primary system boundary at one point. I want to say just a word about the cooling system too, since the sodium system is also one of the important systems. There were actually several systems, as with all these schematic diagrams I'm using, things were often more complicated than that. There were pipes and pumps and valves that had to be in the system, and it was quite complicated. In the sodium system, there were fill systems and auxiliary systems and purification systems that ran with that. But the primary sodium ran through the core, was pumped through a heat exchanger, and that was a closed loop. The sodium did not penetrate elsewhere in the system. A secondary loop of sodium, an intermediate loop, sodium that did not go through the reactor core, then provided an interface between the heat in the reactor and radioactive materials and the power generation system. And in the case of SRE, 20 megawatts was sufficient to actually generate some significant power. And there was actually a Southern California Edison steam generator and turbine system that provided some electricity when the reactor was operating at sufficient power levels. Obviously, this was intermittent. This was a test reactor, but there was a capability to actually provide some electricity. When the electricity was not being generated or was not needed or powers were too low, the heat was generally dumped through simply a air blast heat exchanger. You simply dump that heat so you could cool the sodium coming back into the reactor. I wanted to just talk about at least general design points, because this will come up in the discussion of the accident. As with any nuclear reactor design, the attempt is to provide multiple barriers, defense and depth, for the barriers to fission product release. The concern you have with the safety of any nuclear system is containment of the radioactive material that's generated in that system. And in these systems, the radioactive material generated in the core is generated inside this heavy uranium metallic element. And that element then is a matrix that traps most fission products as long as that material is solid, as long as that material is unaffected. So the first barrier to release of these fission products that's created in the energy generation process is the fuel. And as long as, but if the fuel has melted, then many of those fission products are available to be released. So the fuel is the first barrier. Obviously, if there are materials that get out of the fuel and the clad is still intact, then the clad forms a second barrier. If the clad is breached, and in this case in SRE, where there was actually localized fuel melting, the clad was obviously breached at those places, then those fission products, those reactive materials, those radioactive materials are available to be released to the sodium. The sodium is not a barrier in the usual sense, but the sodium is a very reactive material. It reacts with many of the fission products and at least provides a retention mechanism, a means of limiting the amount of material that gets into the cover gas. And the quantity of that and the phenomenology that goes with describing that will be something I think all three panelists will address. And of course, if it gets into the cover gas and things like the gas fission products that are inert that don't react would get into the cover gas, then the vessel itself and the primary boundary piping is the barrier. So these multiple barriers are what we concern ourselves with when you try to look at the integrity of this system from a safety standpoint. I'm going to do one of these slides out of order. Since we're going to talk about radioactive materials and fission products, I'll apologize for a simplified view graph, but this is a view graph simply to talk about where these materials come from. In the fission of U-238, or 235, when a neutron hits that nucleus, it causes a reaction, a fission reaction, which essentially splits that nucleus into two products. And when we talk about fission products or radioactive materials generated in fission, we're referring to these fission products, these fission fragments that are a fraction of the U-235 nucleus. The mass of those things plus the extra neutrons that come out add up to the original nucleus here. The energy from a nuclear reaction is primarily in the kinetic energy, the energy of motion of these fission fragments. They are born with very high energies. They slow down in the fuel matrix, and that's what generates most of the heat. The nucleus themselves, though, these fission products, are also born with a lot of excess energy. They come into being with a lot of excess energy, and they typically show that as radioactive decay energy. Many of them decay very rapidly down through a series of events into other fission products. Generally, each time it decays, you lose some of the energy and it becomes more stable, so the half-life becomes longer. I think there is an illustration of these decay chains in the panels on the outside of the, you can look at it at the break time. But this complicated series of things still leads to a very wide range of fission products. There are over 400 fission products that could occur from this reaction. One of these two fission fragments could be one of 400. So it's an extremely complicated list of things to consider. So we'll talk about them today in terms of classes of things. The kinds of things that are created here are things like iodine-131 and xenon-133, two of the fission products we'll consider today. Strontium-90, they come with a range of half-lives. These can be seconds, fractions of seconds to years, or hundreds of years. But this spectrum of fission products we'll try to group in generally simpler classes to talk about them in a more convenient fashion. One other point I wanted to make while we're here is simply that the excess neutrons that come out of this reaction, one of those neutrons, if that's reabsorbed in another uranium atom, that is what propagates the chain reaction. As long as one of these can be absorbed in another uranium-235 atom, the fission reaction proceeds at a constant level. If for some reason one of these extra neutrons is absorbed in another medium, and that's what a control rod does, is absorb some neutrons that are born in this reaction. That tends to slow this reaction down. That will cause less fissioning in the isotopes down the road, and it will end up with a lower power. Conversely, if you take some of that absorber out and there are more neutrons available to fission, then that increases the power. And when we talk about control rod motions to raise the power or lower the power in the reactor, what we're basically talking about is absorbers that take one or more of these fission neutrons out of reaction or put it back into reaction. So next I'd like to kind of quickly get into the accident description. The diagram shown on the top is one we took from one of the original reports. It's a simplified diagram just showing the kind of operations. The timeline is shown across the bottom. The power level of the reactor is shown on the emphasis at the top here. So this is a period of 1958, 1959. July of 1959 is out on the edge of this. Run 14 is the one we'll talk about. And I only wanted to say a few words about the previous runs because I think they set the context for what went on in the actual accident. As the name implies, the SRE was an experiment. It was a first-of-a-kind device, and operations were not always exactly as planned. And maybe the first time something significant happened that has meaning for the overall accident was back in Run 8, which was about 6 months before the accident. Operators were running in this run. It included high-power runs. By the way, these power levels are only schematic. They are indicative of the levels of power there, but there were many startup shutdowns within this this period of time where these black histograms appear. They observed early in the Run 8 that they were getting higher temperatures. They were running the reactor at a certain power. The temperatures were actually higher. They noticed that by observing fuel channels and different things. Some channels were higher than others. They were concerned about oxygen. They had opened up the system many times. There was oxygen contamination that produces sodium oxide, a solid material. And they were concerned that there was solid material blocking some of the fuel channels, or at least interfering with some of the heat removal from the system. When they took this out to look at it, they found a black residue on some of these fuel bundles. They removed that, they washed that, and that tended to improve it. They also found by simply moving these fuel rods that could improve the consistency of the measurements they were seeing. The interpretation of that, of course, is there was foreign material in the coolant channel, and this was dislodging that material so that coolant flow was more consistent. The high power run discrepancies, the temperature discrepancies, continued to show up in Run 9. In Run 11, which was this one down here in March, they saw this was a very high power run. They saw continued exit temperatures that were higher in some channels than others. This is a time when they actually stopped. They washed elements. They took them out and actually inspected them and found that at least at the end of that run, they did not see any damage. I think there were some 20 elements that were removed without seeing damage here. But then in Run 13, which was the last run before the accident run, they continued to see escalating temperatures, but these were actually showing increases in time. They would actually be running the reactor and at a steady state, and the temperatures would increase in time. The reason for going over this is not to talk about these particular runs, but just kind of the context that was there. This was a reactor that was operating with a lot of issues. There were helium flow, pump issues, blockage issues that they were aware of. They had also, back in this January timeframe, detected naphthalene in the cover gas, something that shouldn't have been there. And that was interpreted as coming from the organic coolant that actually cooled the pump. And that's an important feature. The organic coolant that actually leaked into the system is the reason for these kinds of effects. So this pump, which was pumping sodium into the bottom of this, was leaking organic coolant, and the organic coolant decomposes in the sodium it forms a variety of compounds, hydrogen, more stable aromatic compounds, but it also leaves a kind of a fine carbon particulate. I may have done that, not sure. So it leaves a fine carbon particulate, and that carbon particulate is what was coating the surface of the reactor and eventually collecting as the flow would go up through the flow channels into the reactor coolant channels themselves. And when they were moving fuel rods to try to improve the operation of the reactor, they were dislodging some of that fine particulate carbon material. They describe it in many different ways in these old reports, but a spongy, porous, carbonaceous material, not completely blocking things, porous to the flow of sodium to some degree. And I'm sure that although not every channel was shown to have a blockage, most channels had some of this material in it. So this restriction of the flow to the coolant channels then led to higher temperatures. Just because the coolant is partially blocked, the power is still the same in the reactor. So with less coolant going by, the temperatures in the fuel heats up, and in some cases it heated up a significant amount. And we collected several graphs of this that we'll show, but I just wanted to say, at the end of that last run, there was sufficient operational difficulties that there was an attempt to shut down the reactor and actually remove some of the organic material. They had a process to bubble nitrogen through the sodium in an attempt to remove much of the organic material. So that was done in this period before the run. On July 12th, when they started up the reactor run, it was after that. Early in the first day of the run, still at relatively low power, they saw significant activities in the high bay, meaning in the space above the reactor in the large room. They attributed that to a shield plug leakage, but clearly there was significant amounts of radioactivity in the cover gas that leaked into that. That apparently cleared away in the next few hours. They were able to replace that shield plug, repair the leak that was there, and then they started up again on July 13th. And the reports described this startup at that point as cautious. They had a series of very unusual events. They started up as cautious, and they were only in the range of a few megawatts by the afternoon of that day. In the process of trying to raise the reactor power, they were raising the control rods to increase the reactor power, and it was observed that the power rose more rapidly than they were expecting. They inserted control rods to reduce the power again, and at that time, then after some delay, the power actually dropped quite a bit more than they were expecting. Then they tried to raise the control rods again to increase the reactor power to the operational requirements, and the power went on a very rapid power rise called an excursion. They actually saw a much more rapid power rise than was indicated by the control rod movement. And of course, the interpretation of that is, now you're finally getting to the point where these blockages are complete enough, where there is voiding of sodium in the reactor that is being removed when the power goes up. The power then rises. When they put the reactor control rods back in and finally get the power down, the sodium refloods. It's colder, the sodium refloods and comes back into the reactor. So the sodium boiling and reflooding is kind of acting like an amplifier on the reactor power. It is magnifying the power fluctuations. This would be a significant red flag in the operation of any facility when the responses of the system are not consistent with the input controls. Nevertheless, the reactor, after consideration, they started the reactor back up on the next day, again at very low power levels, with the attempt to try to understand what these fluctuations were. At least from reading these records, it appears like they continued to operate. There were many startups and shutdowns, but they continued to operate. Finally made an attempt during the later part of this to operate at much higher powers. And somewhere in this period, and I'll show you at least where I think it was, there was damage to something like 13 of the 43 fuel rods. That led to a compromise of not only the fuel, but the clad. Fission products were released into the sodium and into the cover gas. it's actually a little easier to talk about this accident during this 2-week period. And this, you think of an accident, you think of a short time activity, but this is actually an activity that lasted over a period of a couple of weeks. This is a composite of several temperature histories that we put together. So the precision is not exactly right, but I think the sense of it is exactly right. The bottom figure, this blue, is the power level of the reactor. These were the initial power runs. I would assume that this spike is the excursion that occurred early on July 13th. There was some additional runs after that in the 14th, but most of these runs after that were very low power, trying to understand what the behavior of the reactor was. When you look at the temperature profiles, this includes some temperature profiles from both elements that turned out to be damaged and some that did not. The black line is the temperature of the fuel that was in the reactor in channel 55, and that was one of the more severely damaged fuel elements. It shows that the power is continuing to rise even at power levels that were not increasing. You see some evidence that the temperature in that fuel element is continuing to go up. I would interpret that as meaning the blockage is becoming a little more complete, that more carbon particulate is collecting in those channels, causing higher temperatures yet in this, because you see a fairly strong indication here with only modest changes in power. For these higher power runs in July 22nd and 23rd, then that led to a very high power operation, which resulted in very high temperatures in some channels. And in channel 55 at least, these temperatures got well above 1400 degrees. The normal operating temperature at full power for this reactor, the sodium would be in the range of 900 degrees, the fuel would be in the range of 1000 to 1100. So this is several hundred degrees degrees F above the normal operating temperature of these fuel elements. The temperature, however, at 1400 is still well below the melt temperature of uranium. Uranium melts at 2000, so there is still significant distance between the melt of these that happened here and the uranium melt of the fuel. The 2000 degrees for uranium is up here. And what was interpreted at the time, and correctly so I think, and is still considered to be the right mechanism, is much like antifreeze, which freezes at a much lower temperature than either of the constituents that go into it. This is called a eutectic formation. Steel, the stainless steel clad with the iron and the uranium, they form a low temperature melting alloy too. So this alloy, when the steel and the uranium are together, melts at temperatures of 1400, even though steel doesn't melt till 2800, uranium doesn't melt till 2000. So this low temperature melting is what then was going on during this high temperature period. The melting then clearly compromised the clad. The clad was alloyed with the uranium. That material in some cases flowed down the fuel channel, probably increasing the blockage at that point. When you compare that to temperatures that were of undamaged fuel, channel, was that 67? I think it's 67. That is the yellow line here. That is one channel that was not damaged. So the difference in these two channels is both of them saw some temperature rise. It is likely that both had some degree of carbon material in those channels, but only one, the channel 55, was much higher. I think the interpretation of this was identified right after the accident when they first looked at this damage. This low temperature melting alloy was identified at the time and correctly diagnosed. There were also elements that were discovered that were damaged, but there was no melt. At least there was no indication of melt. When you look at these traces of temperatures at these high levels, there were significant variations. As plugging would occur and then unblock, there were significant oscillations in the temperature. And just below this temperature, when the uranium cycles through those temperature ranges, it actually, this thermal cycling actually causes an expansion. It goes through a phase change. And this expansion then eventually works and fails the clad. So of these 13 elements that were damaged, there were 10 of these that showed significant evidence of fuel melting in these regions with the clad, along with clad failure. And then there were 3 that were indicated that they did not see evidence of fuel melting, but they did see the clad fail, so that there was a compromise in the clad. They shut the reactor down after this last run on July 26th. I think they took one of the first elements out. It was one of the elements on the outside of the core, not where you'd expect to have the most damage, and they saw significant damage from partial fuel melting and clad failure. This is pictures of that. If you look at this diagram on the lower left-hand corner, the ones in blue are the ones that were found to be damaged. These are the 13 that were found to be damaged. I think the first one they looked at was one of these on the very outside, typically one you would think would operate at a colder temperature because it's on the outside. But there was significant damage in that. What you see here is just a section of that fuel element, but you see the uranium and steel alloy that has formed, and if the heat is there to flow down the element, what you see, these wires there, that's where the element has been damaged. Those are the wire wraps that were around the element. They've now been freed by breaking of those elements. So significant damage in these, clad compromise, significant damage. When you look at the pattern, it's not really apparent that there was a pattern to the blockages and the damage that formed. These blue things, the blue dots that signify damaged fuel elements, they occurred on the outside just about uniformly with the inside. Normally you'd think the inside, which runs hotter, would be more significantly damaged, but I think it had more to do with how complete the blockage was and how the carbon particulate flowed into the system than it had to do with fuel slugs. After they pulled this out, there were regions that were melted that of course allowed the fuel elements to come apart. But many of those fuel slugs in the top or bottom in the colder regions were not melted or not damaged in means of compromising the integrity. So you see some of those fuel slugs lying on top of the core after they had tried to remove this. A formidable challenge to improve. I included this slide. This is kind of a summary of what was observed in 1960, 1959, and 60. This is from a report by Hart that tried to summarize where they thought the fission products were at the time of the accident. These have to do with what kind of fission products got into the cover gas and were gaseous, what kind of fission products got into the sodium, and what eventually was vented out the system. The observation made at that time was that the noble gases, which of course come out readily, they come out as soon as the fuel has lost integrity. They are not contained in anything. They do not react with anything. If the fuel has melted, they're going to be out in the system and out in the cover gas. He estimated that about 1% of those, I think the number was 0.7%, had escaped the fuel region and was in the cover gas. Several times in this report, the statement was made that iodine, meaning the more volatile fission product, was not detected. Iodine was expected to be there along with cesium and other volatile fission products, but it was not detected. In the sodium, the materials that got into the sodium, the different fission products, of course, behave differently, but most of them were there in proportion to about the level that they would vaporize in the fuel. The gases, of course, that are always gases like noble gases go right through the sodium, but the volatile fission products like strontium, cesium, iodine, many others, those should have been released to the sodium, and they found them all. And they found them about in the proportions they were expecting. The non-volatile species were there in significant amounts. The volatiles were also there. The one thing that was observed in these initial reports was that iodine was there in much lower concentrations than they were expecting. And that was one of the issues. And at least at the time of that report, that was still considered to be a significant issue. They also looked, because they didn't find iodine in the sodium, they also looked at the piping down the road, down the coolant channels, and they assayed that to see if the iodine was there. And again, they found significantly less iodine downstream than they expected. They found the cesium, strontium in the expected amounts, but they didn't see the iodine. So that, at least in the report that I used here, that was still somewhat of an uncertainty in this analysis. They also looked at this carbonaceous material, the blockage material. That was found to be a very effective collector of these fission products. The activities were actually about 1,000 times higher than the sodium itself in these fission, for these fission products that were released in the accident. However, the volume of that was not considered to be sufficient to actually account for any of the loss of the iodine or other things. So although it was considered to be a good collector, it was not an explanation for the iodine that was not found. What we did in kind of looking at this is kind of looked at these observations that were made at the time and kind of do the sanity checks to say, are these reasonable? Are the mechanisms that were encountered reasonable? And would we come to any different conclusions about the release of this material today? The first thing we did was simply to recalculate the inventory, estimate the radioactive inventory at the time of the accident so that we could estimate how many fission products were there to be released. Then after that, we then started looking at the fission product release mechanisms to see if those accounted for any of these anomalies. The fission product inventory, an estimate of the total amount of fission products that were in the reactor at the time of the accident was of course made back in the 1960 time period to try to provide a source term, a starting point for these reaction products. When we did this with our current tools, these are the standard Department of Energy Nuclear Regulatory Commission tools for estimating the radioactive inventory. Those calculations run in Sandia ended up with numbers that within the uncertainties of specifying this problem are substantially the same. We ended up with about 10% less, something like that. However, there is uncertainty in exactly when reactors started up, shut down, how long they were there. So there's some uncertainty. We would consider 10% not an important difference, particularly for the noble gases that were important. They were very much the same number. Things like iodine and cesium, we actually calculated a slightly higher iodine concentration than the original reports did. Other species like zirconium, which are probably not a key factor in the release, were quite a bit lower. So our analysis of these fission product inventories was that the analysis they used in 1959 was reasonable. It was in the ballpark of what we expected. Just going to talk a little bit about the fission product release mechanisms. As I said, the noble gases are inert. It's things like xenon, krypton, same family as helium, argon, neon. These are things that are always gaseous, always released. They don't react with anything. If they're created in fission and there's a way to get out, they'll get out. And these were estimated to be out. And the way we looked at the sanity check here was, it was very difficult to interpret the releases at the time. They were done under varying conditions. It was hard to recreate the release and try to quantify that release. What we did do is try to estimate how much of the fuel melted, because the fuel melt is one of the key factors in determining how many of the noble gases or anything else gets out. If the fuel doesn't melt, the release is relatively low. It gets higher as temperatures get higher, but you don't get major releases until that fuel loses its composition. So we use the melt fraction as an indicator here. And since something on the order of 13 out of 43 were melted, the melt is actually also limited by the amount of steel in the system. There's about 50 times more uranium in the system than there is steel. So the volume of steel then limits how much of the uranium can melt, because you need both components to be present in the alloying formation. And if you take kind of an upper limit of that, you could have said that in the damaged fuel elements, up to as much as 10 to 15% of those elements could have been melted. On the other hand, when you look at their pictures from that time period, and I'm sorry I don't have them in this slide, but we do have them in the reports out there. The damage from this, the melt formed at some region where the high temperatures were, that tended to run down this element, but by and large, many of these elements were still primarily intact. So when you try to estimate the fuel fraction, it's uncertain, but I think you can put an upper limit in the 4, 5, 6% range, and I think you put a lower limit in the 1 or 2% range, and it at least says that when they estimated that about 1% of the noble gases got out, that may be low, but that is in the ballpark of this fuel melt fraction. There was enough fuel melt to account for that. There could have been more, but there probably wasn't a lot more, because simply it's limited by the regions in the core that have high temperatures and the amount of steel that's available there to alloy with. So the noble gases, we would conclude, could have been somewhat higher, but the noble gases, if they are released, probably are not the source of the majority of concern from these releases. These noble gases that were released at least primarily through the stack and venting system. They were put in the decay tanks, they were monitored there and released. Of course, there were leaks otherwhere in the system. The shield plugs, other things had leaks, and that can account for some of the release also. And I do understand that in the later stages before this accident, there were other systems put into place to bypass some of those decay tank storage mechanisms, and I couldn't find any information on whether those were significant in this event or not. So you'll have some uncertainty with estimating these releases, but what they released at the time, or estimated to be released at the time in noble gases, was in the range that was supported by the amount of fuel that could have melted in this process. Of course, the non-volatiles, the things like the metals, zirconium and molybdenum and other things that have very high vapor pressures, very low vapor pressures, those are not expected to get out. They melt at temperatures often higher than uranium, so unless there is higher temperatures, those are not vaporized and therefore not likely to be transported out of the system. So those tended to stay in the fuel. They found those in the fuel, they found those in the sodium in about the expected amounts, but amounts that were quite a bit less than 1% because of the low volatility, the low vapor pressure of those things. So at least in our view, the noble gases were released in about the ratios that would be supported by the amount of fuel melt, as were the releases from the non-volatiles, which were significantly less. The iodine release is the issue that we kind of focus some attention on. Iodine is volatile. It's more volatile than many of the other species, and they expected to see this in higher concentrations in the sodium and outside the system. They saw it at lower concentrations. So you start looking at the mechanisms that affect the iodine release. And of course, the first one is when you release iodine into sodium, there's a very strong reaction with the sodium to form a sodium iodide. The sodium iodide melts at a much higher temperature and therefore is not nearly as volatile. So if there is elemental iodine coming out, which melts at 100 degrees, 113, and it reacts with the sodium, it is likely to be in the form then of an iodide, which is much less volatile. And this retention of iodine in the sodium is well known, well understood. And they did see significant amounts of iodine and cesium in the sodium. The iodine that was in the sodium, however, was lower. And when you look at what could be the possible explanations from that, either that iodine got out of the system early and was vented somewhere, it plated out somewhere down the road, it plated out somewhere in the piping elsewhere, and therefore was not available to be in the sodium, or it was retained in the fuel. It just never got out. And it was not referenced in the old reports, but it is a much better understood phenomena now. In the late 60s and certainly in the 80s, experiments with metal fuel reactors showed that the behavior of iodine is different. Iodine will react with many components. It's a very reactive chemical. It will react with other fission products like cesium, but it also reacts with uranium. And in these cases where there's not much irradiation, a lot of the iodine that's created in fission only has access to uranium. And what forms in that case is a uranium triiodide, a Ui3. It is also a very high melting point material, so that it is not readily released. And experiments done in Germany and the US since then have shown that in metal fuels, some of the iodine is trapped in the metal fuel to a significant degree, that the release from that metal fuel is less than it would be from a light water oxide fuel. The oxide does not bond the iodine to the system, but it does occur in the metal fuel. I included some of the references to these kind of papers. None of these mechanisms are ironclad. Clearly, when I think of release of these volatile species, the statement that was made that there was no iodine observed in the cover gas, there clearly had to be some amounts of cesium iodine that got into the cover gas that played it out down the system. The volatility is much lower after you form an iodide or some other material, but there had to be some. And at least my interpretation would be that with all the activity around, it was difficult to detect that. But I really couldn't find a place where they said how they detected the iodine and what their sensitivity was. But I would have expected there to be some amounts. On the other hand, the amount should not have been a major fraction of the iodine. The experiments have shown that if iodine is mixed with sodium, depending on the conditions, how much gas flows across the top, how much temperature is there, how much the iodine is concentrated, that some fraction of that does come off and go into the cover gas. The numbers are typically 1 or 2% for more aggressive conditions, but a fraction of a percent. So there should have been some of these cesium iodine compounds there, but they should have been in small quantities based on these physical mechanisms. So I think when we look at the lower iodine, it was lower by about a factor of 3. The most probable explanation for that lower iodine concentration is that some of that iodine was trapped in the metal fuel, formed uranium iodide that restricted the release into the sodium. Therefore, the amount of iodine in the sodium was less than expected, and therefore the plate out downstream of that was also less than expected. So, last slide, closing observations here. Based on our evaluation of this accident, when you look at the accident itself, what caused the accident, the leakage of tetralin, decomposed tetralin into the channels, it seemed like the documentation that was provided at the time provides a pretty good explanation for that. The mechanisms were understood. I think the fuel damage mechanisms were also identified and understood. The thermal cycling that fractured clad, the fuel alloy, the steel uranium alloy phenomena that led to melt at temperatures well below the uranium melt temperature. I think those things were all identified and understood. What wasn't done, of course, was to do a very exhaustive inventory to show how much exactly had melted or how much it was still in the fuel at the time. We looked for those kinds of data, and they may exist, but at least we couldn't find them. So the conclusions here are that the noble gases came out in amounts that were consistent with the estimated maximum fuel melt fraction. And at least in my view, that is the primary factor in a significant release. There clearly is releases at temperature below melt, but they are small compared to when the fuel melts, then there's a major release. So the fuel fraction kind of limits that, and the noble gas releases were consistent with that. The non-volatile species were found in amounts that were consistent with that also. And at least in this analysis, if you look for an explanation of where the volatile fission products are, it seemed like those mechanisms of retention in the sodium, retention in the fuel, and some limited amount of plate out on the components accounts for the reduction in fission product inventory that was seen there. I think that concludes my remarks, Kevin. I think I will end there. I think I've taken all my time, too.
You have.
Thank you.
Take a break.